Hello everyone. In this video, we're going to talk about the limit comparison test. As you may have guessed, the limit comparison test is very similar to the comparison test that we saw in the last video. We're still going to be comparing two different series, but the method's going to look a little bit different. To explain why the limit comparison test is useful, I'd first like to talk about a problem with the regular comparison test. That problem is that the comparison test simply just doesn't always work. For instance, consider the series sum from n equals 2 to infinity of 1 over n squared minus 1. Let's try to tell whether the series converges or diverges using the comparison test. Well, if we had to guess, we would say that this series should behave something like 1 over n squared. So let's try to compare these two series. To apply the comparison test, we need to know which is bigger. In this example, we see that n squared minus 1 is less than n squared, and so 1 over n squared minus 1 is greater than 1 over n squared. Now, what do we know about the sum of 1 over n squared? Well, we know that it's a convergent p-series. And so, we found a series that's smaller than the series we were given that converges. And so, the comparison test tells us absolutely nothing. Remember, we need either a smaller series that diverges or a bigger series that converges. So it turns out the obvious guess didn't quite work here. We could probably fix this issue by being a little more clever about the other series that we chose, but in general that's really hard to do. And so the limit comparison test is going to help us out a lot here. The limit comparison test says, suppose we have two series, the sum of an and the sum of bn, where all of the terms of both series are positive. If we take the limit of an over bn and get some finite number bigger than 0, then either both of these series converge or both of these series diverge. In other words, both series do the same thing. What the limit comparison test is really doing is making precise this notion of behaves like that we've been using when we come up with our guesses for comparison series. If we take this limit of one over the other and get something finite, this says that towards infinity, one series looks like a constant times the other, and so they have to behave similarly towards infinity. It's not really important that you understand all that, but what is important is that you understand how to apply the limit comparison test. And let's demonstrate how we do that using the example we used above. Let's decide whether the series sum from n equals 2 to infinity of 1 over n squared minus 1 converges or diverges. So in the limit comparison test, we'll take our an's to be the terms of the series that we were given, and we'll take bn to be 1 over n squared, which is the comparison function that we tried to use before but failed. Now we take the limit of an over bn, and after some simplification, we get the limit of n squared over n squared minus 1, which goes to 1. Therefore, these two series satisfy the limit comparison test, and so they either both converge or they both diverge. But we know that the sum of 1 over n squared is a convergent p-series, and so our series converges as well by the limit comparison test. Let's go ahead and churn through a couple more examples. First, let's tackle the sum from n equals 1 to infinity of n squared plus 2n plus 1 over n to the fourth plus n squared plus 2n plus 1. Now, it's probably good to point out here that the series would be an absolute nightmare to deal with using the regular comparison test. Because usually we find our comparison series by dropping off insignificant terms to get something simpler. But here, there's just so many terms that it's not even clear where we start. It turns out, though, that the limit comparison test works exceptionally well for series of this form. To see why, let's think about what our comparison series should look like. In the limit comparison test, we let an be the terms of the series we were given, and bn should be a simpler series that behaves the same way. We'll choose this series in a similar way to how we did for the regular comparison test. We see that on the top, the most significant term is the n squared, and the most significant term on the bottom is n to the fourth. So our comparison series will be n squared over n to the fourth, which is equal to 1 over n squared. Now, to apply the limit comparison test, we need to take the limit of an over bn, and what we get when we multiply these fractions together is the limit of n to the fourth plus 2n cubed plus 1 over n to the fourth plus n squared plus 2n plus 1. Since the top and the bottom have the same degree, we find that the limit is the quotient of the leading coefficients, which in this case is just 1. Therefore, these series satisfy the limit comparison test, and so either they both converge or they both diverge. However, we know that the sum of 1 over n squared converges by the p-series test, and so our original series converges as well. As a final example, consider the sum from n equals 1 to infinity of 1 plus 1 over n cubed times 3 to the minus n. Just like before, we let a and b the terms of the series that we're given, which we can rewrite as 1 plus 1 over n cubed over 3 to the n to get rid of any negative exponents. Now, for the comparison series, we find the most significant term on the top over the most significant term on the bottom. On the top, it turns out the most significant term is the 1, since the 1 over n goes to 0 as n goes to infinity. So, the top of our comparison series should be 1 cubed, which is just 1. On the bottom, there's only one term, which is 3 to the n. So, our comparison series is 1 over 3 to the n. Next, we take the limit of an over bn, and we find that the 3 to the n's cancel. And so we're left with the limit of 1 plus 1 over n cubed, which just goes to 1. So, since the limit is finite and positive, the limit comparison test says that both series converge or both series diverge. However, we know that the sum of 1 over 3 to the n is a convergent geometric series, since the common ratio is 1/3. So, our given series converges as well. Alright everyone, thank you for watching, and have a great rest of your day.